In this lesson, we're going to talk about differential signals, and we're going to compare single-ended versus differential. The single-ended case is when we have a driver and a receiver. We send the signal down the trace, and the return signal comes back on the plane. In the differential case, we send a signal down on one side of a differential pair, and the return signal comes back on the other side of the differential pair. The signals on the two traces are equal and opposite in theory, and therefore there is no signal through ground in theory. We're going to talk about both of those assumptions as we go through this lesson. There are pros and cons to differential signaling. The pros are you get a better signal-to-noise ratio. Ground continuity is not an issue because the signals are equal and opposite, and there is no signal through ground. And you can get very precise signal timing. The cons is that there are two traces per signal, so we have a real estate penalty when we use differential pair. Of these three benefits, I'm going to argue only one of them is really significant. The other are less important and maybe not even real. Now, let's look at these three benefits. First, the improved signal-to-noise ratio. Here's a single-ended example. I've got a driver, I've got a signal, I've got a receiver, maybe this is an amplifier. The amplifier's got a gain. I've got noise radiating onto this trace, maybe in the form of crosstalk or in EMI. I've got noise on the ground plane that I'll call NG. And in the amplifier, I've got a gain, so the signal out is G times the signal, and the noise out is G times the sum of the noise sources. So we can plug some numbers in here to see what happens. The radiated noise is 10 microvolts. The ground noise is 10 microvolts. The signal is 10 microvolts. And the gain is 500. So the output coming out of the amplifier, the noise is 10 millivolts. That's 10 microvolts plus 10 microvolts times 500. And the signal is 5 millivolts. That's 10 microvolts times 500. Therefore, the signal-to-noise ratio is 0.5. Now, let's look at this same thing and the benefit we get if we have a differential pair. Here we have a driver, but we have the two signal traces down and back, and we have two gains in this amplifier. We have a differential gain, so we have the gain times 2 times the signal because we have one signal on this trace and one signal on this trace. And the noise that comes out is the common mode gain times the sum of the noise. Now the differential gain and the common mode gain are two different animals. So here are some suggestive numbers. Let the noise be 10 microvolts again. The ground noise be 10 microvolts. The signal be 10 microvolts. The differential gain be 500. The common mode gain be 0.1. Now, in an ideal amplifier, the common mode gain would be 0. The amplifier would be completely responsive to the differential signal and would completely ignore the common mode signal. In reality, they aren't quite that good, so we'll set the common mode gain at 0.1. Now we look at the output. The noise is 2 microvolts. That's 10 microvolts plus 10 more microvolts times 0.1 gives us 2 microvolts. The signal is 10 millivolts. That's 10 microvolts times 500. And the signal-to-noise ratio then is 5,000. That compared to 1/2 on the previous illustration. That is a significant benefit for differential signaling. Now, I'm going to show you a little simulation that I have, just using a spreadsheet. We're going to have a driver. We're going to have a receiver. We're going to have noise on the traces. And the question is, what comes out at the other end? Do we get noise out the other end, or do we get either silence or just a perfectly clean signal out the other end? And that depends on the source of the noise, whether it's internal or common mode noise. So internal noise would be noise that is generated internal in the circuit. Common mode noise would be noise that comes from outside and is injected onto the traces. Now I'm going to show a little simulation using a spreadsheet to illustrate what happens here. This is a spreadsheet that gives me a couple of windows here now. What I have is I have a driver, I have a receiver, I have the differential pair of traces that are connecting them. There's noise on these traces. The noise is a little bit more than 5 units peak to peak. And then I have a signal between the two traces, and that's what this represents down here, 12 units. And the noise is either going to be internally generated, that's internal in this amplifier, or it's going to be a common mode noise that's generated from the outside, and the amplifier is going to be able to reject it. So right now we're looking at the internally generated noise. With 12 units of signal, I get a relatively straightforward waveform out, and especially if I look at the sign of the output, which tells me whether I have a logical 1 or a logical 0, then I get a pretty clean signal with 12 units here. Let's change this to 8 units and see what happens, and I still get a pretty clean signal. I've got a little bit of uncertainty right here, but that's probably not going to pose a problem. Let's run 6 units of signal, and still looks reasonable. Let's run 4 units of signal, and now all of a sudden I'm starting to get some places where I'm making errors between a logical 1 and a logical 0. Anywhere where I've got one of these spikes, that's an error because the noise is overwhelming my signal. Let's go to 3 units of signal, and all of a sudden I've lost everything. This system isn't going to be working at all with 3 units worth of signal. But let's now do the same thing and assume the noise is coming in from a common mode standpoint. With 12, everything is looking good. Let's go to 5. Everything is still looking very good. Let's go to 4. Everything is still looking very good at the output. In fact, let's go to 1. And everything is still looking good at the output. That's because the common mode rejection of the amplifier is rejecting all of this common mode noise, and the only thing that is getting through at all is the signal. That illustrates the benefit of differential signaling. There's not much of a benefit if the noise is internally generated. But if the noise is common mode noise, then there is a real benefit to differential signaling. Benefit 2 is ground continuity. If we have a positive signal on this trace and a negative signal on this trace, then there's no signal going through ground. The only noise on the ground at all is just noise. Common mode rejection ratio should reject that noise. And so since the common mode noise is rejected, it doesn't matter what the power distribution system looks like, in theory anyway. I'm going to show you later that that argument doesn't necessarily hold. But part of the theory and part of the argument for differential signaling is since the signals are on the 2 traces and there's no signal on ground, therefore we don't care if there's planar continuity or what underneath the devices. The third benefit is signal timing. In the single-ended example, we have the power up here and the ground down here. There's a high threshold above which we know we have a 1. There's a lower threshold below which we know we have a logical 0. And there's an uncertainty region in between. So if our signal transitions from a logical 0 to a logical 1, there is a period of time where we're passing through the uncertainty region, and right in this period of time, we don't know what the signal level is. If we have differential signaling, well, we can say that if the plus signal is above the minus signal, we have a logical 1. If the plus signal is below the minus signal, we have a logical 0. And where that changes is a very precise point. There is no uncertainty region. Now, this argument is true, and signal timing is more precise with differential signaling. Nevertheless, in single-ended signaling, we usually have tolerances that we know how to work with and that are sufficient for our logic devices to work. So while this is a real benefit, it's not necessarily a significant benefit. So of these three benefits, the signal-to-noise ratio, the signal timing, and no reference plane requirement, I'm going to argue that only the first one is really true and is really the most significant one. Now, what is the difference between differential mode and common mode? If you ask people that question, what you're liable to hear is differential mode is when the signal goes down the trace and back on the plane. Common mode is when the signals go the same direction on both the trace and the plane. That's an explanation that you oftentimes hear. Well, before we get too far, I want to also point out that purists will tell you there isn't a differential mode and a common mode. The correct terminology is odd mode and even mode. And so what we would say is in the odd mode, the signal goes down one trace and back on the other. And in the even mode, the signals go the same direction on both traces. Okay? The purists will say that differential mode and common mode are incorrect terms. We read them on data sheets all the time about common mode rejection ratios and so on. So we use these terms all the time, even though they, strictly speaking, may not be the correct terms. But the explanation that the signal goes down and back in this case and the signals go the same direction in the other case is a poor explanation, because that answer is only partially complete. Remember, every signal has a return. If we have this driver driving a receiver with a trace, no signal is flowing. There must be a return path back. And remember that return signals account for most of our signal integrity problems. When we make this argument that common mode or even mode is when the signals go in the same direction on both the trace and the plane, or the signal goes in the same direction on both traces, that doesn't answer the question, where is the return current? And a better definition, in my mind, is differential mode is when the signals go where we expect them to, based on the traces and based on the schematic. Differential mode are the signals that we expect to be there and that we actually plan for. Common mode are all the other signals. We didn't plan for them, and frankly, we don't even want them. Now, we can break any signal situation into its differential mode and common mode components. For example, let's assume we have a 10 milliamp signal. 9.95 milliamps returns where we expect it to, and 50 microamps returns by some other path. That is common mode. So that 50 microamps is going to divide into 25 microamps on the trace and 25 microamps on the plane. That leaves 9.975 milliamps going down this way and coming back again on this side, because the sum of these is 10 milliamps and the sum of this is 9.95 milliamps going back. And if we look at the differential mode case, we get the same sort of situation looking this way with 50 microamps coming back through some other path. Now the question is, where is this 50 microamps flowing? These common mode currents can be flowing somewhere that might be quite detrimental. So here are the questions. Where are those common mode currents? What's the problem with them? How do they originate? And how do we control them? Those are all very good questions. And the answers are, and maybe not fully satisfactory, we generally don't know where these currents are. That's the problem. And the problem is they can generate EMI because we now have uncontrolled loop areas. They occur typically by accident or by sloppy design practices, and throughout the remaining lessons we'll talk a little bit about how that can happen. And we control them principally by, number one, preventing them from happening in the first place, or if they do happen, and they will, shorting them out with capacitance. And the capacitance that we use to short them out comes from bypass capacitors and planar capacitance. And that leads to a new design rule. To prevent common mode generated EMI from being radiated, use planar capacitance. And that comes from power and ground planar pairs. Our first primary design rule was route every trace as close as practical to a continuous related underlying plane. The second major design rule is use planar capacitance from power and ground planar pairs. The takeaways from lesson 4.1. The primary benefit of differential traces and signaling is improved signal-to-noise ratio. There's also improved timing, but that's typically not a terribly important benefit. Common mode currents are usually not designed in, but they exist because of poor design or factors and tolerances beyond our control. Common mode currents can cause EMI problems, and in fact, I've heard experts say that probably 80 to 90% of EMI is caused by common mode currents, not by differential currents. And our second most important design rule is to add planar capacitance to help short out these common mode currents. In lesson 4.3, we're going to talk about PCB design rules that relate specifically to differential signaling and traces.